In the previous section, we saw how the max-cut problem can be mapped to an Ising Hamiltonian. We transformed a graph partitioning problem into finding the ground state of a quantum system. But we left one crucial question unanswered. How do we actually find that ground state? This is where the Variational Quantum Eigensolver, also known as the VQE, comes in. VQE is a hybrid quantum classical algorithm designed to find the ground state of a Hamiltonian, which, as we have seen, encodes the solution to our optimization problem. While it was initially developed for quantum chemistry application, it is equally powerful for optimization problems like max-cut. The beauty of VQE is it's designed specifically for noisy intermediate scale quantum computers, the imperfect devices we have today. Remember, for the max-cut problems, we constructed an Ising Hamiltonian. The ground state of this Hamiltonian, the quantum state with the minimum energy, encodes the solution. Finding this ground state is our goal. So, for a graph with n vertices, also n qubits, there are 2 to the n possible configurations to check. For just 50 vertices, that's over 1 quadrillion possibilities. Classical computers hit a wall very quickly. But quantum computers can explore this space efficiently using carefully designed algorithms. VQE is built on one of the most fundamental concepts in quantum mechanics, the variational principle. Formally stated, the expectation value for h is always greater than or equal to E of 0 or E naught, which represents the ground state energy. Let me explain what this means. Ket of psi theta is any trial quantum state parameterized by variable theta, like rotation angles in quantum gates. H is our Ising Hamiltonian, and the expectation value for H is the energy expectation of that trial state. This expectation value will always be greater than or equal to the true ground state energy E naught. This is incredibly powerful. No matter what state we prepare, measuring its energy gives us an upper bound of the ground state energy. The closer our trial state is to the actual ground state, the lower the energy. Remember, we want to maximize the cut value C of x in a max cut, but quantum systems naturally minimize energy. That's why we defined our Hamiltonian as h is equal to minus C of z. When we minimize h, we are maximizing C of z, which is exactly what we want. The variational principle guarantees that by iteratively adjusting our trial state to minimize the energy, we are finding the maximum cut. Here's the 3 components of VQE. First, we have the ansatz. The ansatz refers to the trial quantum state, ket of psi theta, parameterized by an array of variables theta. Think of the ansatz as your educated guess for the solution, implemented as a parameterized quantum circuit. The parameters theta are typically rotation angles. The quality of the ansatz is crucial. A well-designed ansatz can find good solutions quickly, while a poor ansatz may require many more iterations or fail to find the optimal solution at all. Second, we have the measurement. Once we've prepared the ansatz state, psi theta, on the quantum computer, we need to evaluate its energy. How good is this trial solution? Ansatz is run repeatedly for m times For each run, the n qubits are measured yielding measurements values zi of k, where zi of k is equals to +1 for measurement outcome ket of 0, and zi of k equal to -1 for measurements outcomes 1. We are essentially measuring each qubit with the z observable, also known as the poly-z operator. Then the expected value of the Hamiltonian is estimated according to this equation, where the first sum runs over measurement runs k and edges ij element of E, and the second sum runs over measurements run k and vertices I element of V. Ising Hamiltonian involves only z operators and is diagonal in the computational basis. Since z ket of 0 is equals to ket of 0 and z ket of 1 is equals to negative ket of 1, we can directly compute the energy from computational basis measurements. After measuring the quantum state and estimating the energy expectation value, we use a classical optimizer to propose beta parameters. The optimizer's job is to find parameters values that minimize the expectation value of the Hamiltonian. Common classical optimization algorithms include gradient descent, which follows the slope downhill, COBYLA, also known as the constraint optimization by linear approximation. Here, no gradients are needed. We also have the SPSA, simultaneous perturbation stochastic approximation, which is efficient for noisy measurements, as well as the Nelder-Mead, which is a simplex-based optimization. The classical optimizer updates theta to theta nu, and we repeat the process. Here's how VQE works in practice for solving max-cut. Design a parameterized quantum circuit that serves as the ansatz ket of psi of theta. Start with all qubits in the ground state. Apply parameterized gates controlled by theta and run the circuit and measure the qubits. Repeat m times to get statistics. Compute the energy expectation classically using the measurement results. And classical optimizer proposes new parameters based on the computed energy, which adjust theta to reduce the energy. Then send the updated parameters back to the quantum computer. Repeat until convergence or until the change in energy falls below a threshold. Here is the flow. The quantum computer prepares and measures states. The classical computer processes measurements and optimizes parameters. That's true hybrid computing. The edge weights W of ij from our max-cut problem are not incorporated into the variational parameters theta. Instead, theta is used to construct the trial quantum state within the quantum second. The weights W of ij are used to compute the expected energy value on a classical computer. The classical optimization routine uses this energy to iteratively adjust theta. This separation is crucial. The quantum computer explores the quantum states while classical computer handles the problem-specific weights and optimization logic. When implementing VQE, keep in mind the number of measurements. More measurements give more accurate energy estimates but take more time. Also take a look at the ansatz depth. The deeper the circuits, the more complex states, but they are more prone to noise on NISQ devices. You should find the right balance. Also for the optimizer choice, some optimizers handle noisy objective better than others. And for the convergence, VQE doesn't guarantee finding the absolute optimal solution, which is the global minimum. It finds good solutions, often near optimal, which is valuable for NP-hard problems. So how does VQE compare to classical algorithms for max-cut? For classical algorithms, exact solutions are exponentially hard. Heuristics like simulated annealing can find good approximations, also scales poorly as the graph size increases. As for the VQE, it uses quantum superposition to explore solution space, can potentially find better solutions faster for large instances, and it is currently limited by qubit count and noise, but improving rapidly. The quantum advantage becomes more pronounced as problem size increases, especially for graphs with complex structure where classical heuristics struggle. VQE represents a pragmatic approach to quantum computing, leveraging what quantum computers can do well, which is exploring large state spaces while letting classical computers handle optimization and control. It's not waiting for the perfect quantum computer. It's extracting value from the imperfect ones we have now. Next, we will explore QAOA, which is the quantum approximate optimization algorithm, which takes a different approach to the same combinatorial optimization problem.